Finding the center, vertices, and foci of an ellipse. Find the center, vertices, and the foci of the ellipse. Simplify your answers as much as possible. First thing I'm going to do is let's just draw a really rough sketch. Let's turn on our Google location, and let's put the center of this ellipse with a little blue dot or a little blue asterisk. And that is, of course, labeled 3, 1. And the major axis is always it's always twice the A value. And in this case, A is 5, and then B is 3. And the major axis is actually running horizontally because it's under the X values. So we're going to take this major axis and just draw it longer than the minor axis. So here's your rough sketch of the ellipse. Because it's stretched horizontally, you do have two focus points, or we say foci for plural. So right about there and there. You know, that would be one focus point and another focus point. Where are your vertices? Your vertices would be at the end of your major axis. Alright, we already have the center, so that's great. Why don't we write that down? Center is sort of the location of your ellipse, so it's going to be located at 3, 1. Now keep in mind, the center is never part of the ellipse, it just locates the ellipse. The black part here is actually the ellipse, right? The black part. We also need to find the vertices. Well, how do we find the vertices? We're going to go 5 units to the right from the center. So how can we write that? Vertices are going to be 3 plus or minus 5, 1. Now this is not preferred. It's better to separate the vertices so that you could see two ordered pairs. So let's say -2, 1 and 8, 1, and we put a comma right here. So that those green dots there are labeled -2, 1. I say -2, 1? Yes, -2, 1 and 8, 1. All right. Only thing left to find are the foci, or the two focus points. We do have an equation for that. So if you look at this, why don't we draw this part? There's a little triangle right here. And right there. Ah, gorgeous. So remember, this is the side A, and this is the side B. And I could still relabel this. Remember, that was the what? That was the center. A is always more than B, and to get the foci, the location of the foci, we follow this formula. We're going to use c squared is equal to a squared minus b squared. And in this case, the foci are running in the horizontal direction. So what would we write? You could think of the formula as 3 plus or minus c, 1, right? And where did I get that from? I remember you're finding the foci relative to the center. So that's why that location is very important. Obviously, c is defined to be what? Greater than 0. It's very important that you write this. C is defined to be greater than 0. A is 5. B is what? 3. So you know that A is greater than 0 and B is greater than 0. Now let's look at c squared. C squared is equal to 25 minus 9. now we got 16. C squared is equal to 16. Square root of c squared, and then square root of 16. By definition of the square root of c squared, that's the absolute value of c. Absolute value of c is equal to 4. And if we do that, c must be what? Plus or minus 4. And we know c is greater than 0. Therefore, c is 4. We could now find our foci. Therefore, foci are what? 7, 1, and negative 1, 1. There you go. I'm going to circle all our final answers. The center, we need the center, that's what it asked for. We also need the vertices. I guess I could say are the vertices here. And the vertices of the major axis. So if it doesn't specify the axis, it's implied that you're finding the vertices of the major axis. Now, key work that needs to be shown. If you're solving this equation here, c squared equals 16, most people will show their work like this. And so I'm going to be looking for this work. That's going to be crucial. Don't ever change the steps for solving a quadratic equation of this form, right? You don't change the steps there. You know, if c squared equals 16, you know, you should be able to show plus or minus 4. There's other ways to show that. You don't want algebra to be miscommunicated from semester to semester. Algebra has been the same for hundreds of years. Right? I mean, you could see that this is another way to get what? C is equal to negative 4 or C is equal to 4. I skipped a step. There. That should make things clear. So there are many ways to show the algebra correctly. Make sure you do algebra correctly. After all, this is algebra. Writing an equation of an ellipse given the center, an endpoint of an axis, and the length of the other axis. Find an equation of the ellipse that has the center 1, 4, a minor axis of length 8, and a vertex at 1, negative 8. To get a better idea of what's going on, let's take those 3 hints and make a rough illustration. Why don't we start with the center? Typically, we could put the center as a star. It's going to locate our ellipse. I'm going to label that 1, 4. A vertex, remember, is an endpoint on the major axis. And the major axis is always longer than the minor axis. So where's 1, negative 8? Well, let's say 1, negative 8 is here. Let's make a dot. And let's label that. Let's label it this way. 1, negative 8. So I do need to know this distance. If I know this distance, this is going to be our A distance. We could simply count that. We could always do big minus small. So that distance is 4 subtract negative 8, and that is 12. So we know A is 12. The minor axis has length 8. So if we take this information here, we know that B is 4. So we have A is equal to 12, which is more than B, which is equal to 4. And we have the center already. The center is 1, 4, which we will call HK. And our standard form is x squared, I'm sorry, not x squared, x minus h quantity squared, a is not in the horizontal direction. So let me take that back. Let's erase this. A is actually where? A is in the vertical direction. So that tells me that b squared is underneath the x minus h quantity squared, plus y minus k quantity squared over a squared has to equal 1. Now we substitute everything. X minus 1 quantity squared over b squared, so 4 squared, which is 16, plus y minus k quantity squared over a squared, 12 squared, which is 144. Or I could write 12 squared equals 1. X minus 1 quantity squared over 16 plus y minus k quantity squared over 144 is equal to 1. Ta-da! And that fits the puzzle. Writing an equation of an ellipse given the foci and the major axis length. Find an equation of an ellipse having a major axis of length 12 and foci at 5, 3 and negative 1, 3. Why don't we draw a rough illustration here? The best thing we could draw are actually the foci. So 5, 3. That means this is actually elongated in the horizontal direction. So we have negative 1, 3, and we have 5, 3, and we have something like a rough ellipse elongated in the horizontal direction. And so this is a rough sketch there. Now in between here, it looks like that has a distance of 6. So if you cut that in half, so if you count 3 units to the right of negative 1, we actually get the center. It's not the greatest ellipse here, but like I said, it was going to be a rough illustration. So count 3 units to the right from negative 1. 0, 1, 2. So this is 2, 3. And now we have the center. That is awesome. HK, or parentheses HK, is equal to parentheses 2, 3. Now, the major axis, remember, is equal to 2a. So 2 times a is equal to 12. So a is equal to 6. The only thing left to find is b. And we have a relationship between the distances of the foci from the center and the half the distance of the minor axis and the major axis. And it's related by c squared is equal to a squared minus b squared. Do we know c? We actually know c. We counted it earlier. It was 3, right? Yes, c was to be 3. I could label it in the picture if you want. That is c right there. C is also positive, it's 3. So we could actually solve for b. B squared then would be what? A squared minus c squared. And b squared is now equal to, let's see here, 36 minus 9. So b squared is equal to 25. Taking the square root of both sides to this quadratic equation, we get the absolute value of b is now equal to 5. That means b is equal to plus or minus 5. And we know what? By definition of an ellipse, b has to be greater than 0. Therefore, b is 5. what do we have? We want to write our standard form of an ellipse, and that's elongated in the horizontal direction. So we have x minus h quantity squared over a squared plus y minus k quantity squared over b squared, which is now equal to 1. So x minus 2 quantity squared over a squared, which is 36, plus y minus 3 quantity squared over what here? Over b squared. Where's b? B, we got 5, so it's 25 is equal to 1. And there you go. You got the standard form of this ellipse. Make sure you show some really key algebra steps here. You really have to show this step and this step right here. If you are taking calculus classes in the future, you want to show all these steps right here for sure. I mean, you always show your work neatly and orderly anyway, but make sure you know how to solve that type of quadratic equation. A word problem involving an ellipse. The curved edge of the doormat below is half an ellipse, a semi-ellipse. As shown in the figure below, the flat edge of the doormat measures 164 centimeters, and the distance from the center to the curved edge is 52 centimeters. The distance from the point P to the curved edge is 11 centimeters. Find the distance from P to the center. Round your answer to the nearest hundred. Do not round any intermediate computations. If you take a careful look at your picture, this was the given picture. Unfortunately, it's clearly not the scale. It's not a very good picture here. So if you notice that, you might want to draw it to your own scale. You can actually redraw it. And do the best you can. I mean, there's the ellipse or the semi-ellipse. So the black line here is representing the major axis. The problem I have here is that the 52 centimeters is down here, but 11 centimeters is only 1/5 of that. So 11 centimeters should be about here. So that means point P is really about here. So this would be probably a better scale. Now your center is really important. We're going to use a technique that's used in physics and in calculus a lot. You actually have to locate your own center. And you want to pick your center to be very convenient. I just drew a dotted axis. I'm going to call that axis the x-axis. I'm going to draw another dotted axis here. And that is going to be called, of course, the y-axis. So what's a convenient location? Let's use our classic blue dot or blue star. And let's call that to be the origin, 0, 0. And that will locate your doormat. It will give location to every single point on the ellipse now. This is very convenient. You're given the major axis already. So from here to here, you know how much this is. This is actually 82 centimeters. You're also given the minor axis. The minor axis from, let's say here, if I drew this solid right now, this is actually 52. And of course that is equal to B. And 82 is equal to A, according to our standard forms of an ellipse. So that's fairly convenient, because now you could actually label this. Labeling is a mathematical skill. Drawing is a mathematical skill. You want to draw and label this to be what? P, comma, -11. And how do I know it's -11? Because you, yourself, drew the origin right here. So you got to label this relative to the origin. So that is going to be the distance p right here. From here to here is p. This is what we're looking for. Why don't I highlight it in yellow? This distance here is what we're looking for. And that is going to be called p. All right. Why don't we develop the equation of this ellipse in standard form? So we have x squared, and we know that a squared is underneath the x squared, plus y squared, and we know that b squared is under the y squared. A is half the distance of the major axis, and the major axis is along the horizontal direction. Now we're going to set this equal to 1, so we have our equation of the ellipse. We're going to take this point right here, and we're going to substitute it in there. What do you mean substitute in there? Well, we're going to have p squared over what? Over a squared plus, what's y? Well, y is negative 11. And what we're going to do with that negative 11, we are going to square it. Put it over what? Put it over b squared is equal to 1. And now we're going to go ahead and solve for p. Let's multiply both sides by the lowest common denominator to clear fractions. So over here, we're going to multiply by a squared times b squared. Over here, we're going to multiply by a squared times b squared as well. So 1 there. What do we have? We have p squared over b squared. Oh, sorry. Take that back. A squares reduce, and we have p squared times b squared plus 121a squared is equal to a squared times b squared. Now we know b squared is not 0. So now we have p squared is equal to a squared times the quantity, b squared minus 121, yeah, all over b squared. I'm going to take the square root of both sides. And you got to remember that a is greater than b and greater than 0. The key is that they're both greater than 0. They're both positive. Why is that really important? We get p is now equal to plus or minus the absolute value of a over the absolute value of b times the square root of b squared minus 121. Now it's very important that you note that a is greater than 0 and b is greater than 0. That implies that the absolute value of a is a, and that implies that the absolute value of b is b. So we got p is now equal to plus or minus a over b times the square root of b squared minus 121. Now we're ready to put in the numbers. P is equal to plus or minus, what was A? 82. B was 52. B squared is, well, 52 squared minus 121. Go ahead and use the order of operations and perform this on your calculator. You should get P here is equal to plus or minus 80 decimal 14431, and of course there's lots of decimal places after that. We're trying to round to the nearest hundredth, so why don't we look at the thousands place? The thousands place is a 4, so we're going to round this down to 14 hundredths. Now, we're really ready to answer this question. Notice that p is greater than 0 as well. So the distance from P to the center is 80 decimal 14 hundredths, right? Or 80 and 14 hundredths centimeters. Circle that. State it like you mean it. Don't forget your labels. Make sure you label centimeters. We're not talking about miles, kilometers. We're not talking about feet. We're talking about centimeters. Some important algebra that you want to look after is definitely some really key steps that you want to show are actually right here. Well, everything. Try to replicate all these steps. I would recommend that you do not skip any of these steps. So try to replicate all of these steps. Every single detail. The arch of a bridge is half an ellipse, a semi-ellipse, as shown in the figure below. The arch is 150 meters long and has a height of 48 meters at the center. The point P is located 17 meters from the center. Find the height of the arch above point P. Round your answer to the nearest hundredth. Do not round any intermediate computations. Well, let's conveniently label the center. Let's label this to be the origin, 0, 0. We also know A value is 75. Remember, A equals 75 is half the length of the major axis. We also know B. B is what? B is equal to 48. Everything's in meters. Well, since things are conveniently located in the center, we do have the standard form of the ellipse. Now, keep in mind, I don't need the entire ellipse. There's actually an ellipse right here, right? We have half an ellipse. But we're going to write the equation of that entire ellipse. It's going to be x squared over a squared, because it's elongated in the horizontal direction, plus y squared over b squared is equal to 1. Now we're going to look for p, and the way we're going to find p is use this value there. That's going to be a key step. We're going to call that ordered pair p, comma 17. We're going to take that p, comma 17 and substitute it into your equation. So x is p and y is 17. Well, if x is p, then we get p squared over what? Over a squared plus 17 squared over b squared is now equal to 1. Now you just react to this and solve for p. Multiply both sides by the lowest common denominator, a squared times b squared, to clear fractions. And we'll do the same thing here, a squared times b squared to the 1 as well. We have to balance the equation. What do we have left? We have a p squared times a b squared plus a 17 squared times an a squared is equal to a squared times b squared. Solve for p. You're going to react to this. We know that b squared is not equal to 0. So p squared is now equal to a squared, factored out here. We get a b squared minus 17 squared And all over what? All over b squared, because b squared is not equal to 0. Take the square root of both sides, and we get the absolute value of p is now equal to the absolute value of a over the absolute value of b times the square root of b squared minus 17 squared. Now what happened there, I just simply used the square root of a squared over the b squared, which is the square root of a squared over the square root of b squared, which is equal to the absolute value of a over the absolute value of b. That's what happened there. We do know what, though? We know a is greater than b, which is greater than 0. A is greater than 0 as well. B is greater than 0. And so what happens to the absolute values? Then they have the absolute value of a has to be a, right? It's positive. What's the absolute value of a positive number? Well, you just get the number itself, because a and b are positive. You do need to state that. Where are we? Bum, 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 bum. So p now is equal to, absolute value of p is equal to a over b times the square root of b squared minus 17 squared. That means p is now equal to plus or minus a over b, square root of b squared. And let's calculate 17 squared minus 289. We know what a is. A was 75, plus or minus, excuse me. We know what b was. B is, I should say. B is 48 times the square root of b squared. We need to know b squared. B squared is 48 squared minus 289. Use the order of operations on your calculator and perform this computation. You get 7.0.1386 and lots of decimal places after that. We know p is greater than 0, and we need to round our answer to the nearest hundredth. So we're going to look at the thousands place. 8 is more than 5. We're going to round this up. And we know that p is greater than 0. And let's say that the distance from p to the center is about 14 meters. Don't forget your units. I am going to go ahead and circle the final answer. Make sure you could replicate all the work on this page. You need all of it. You need this ordered pair here as well. I should circle that too. We're going to go ahead and graph this hyperbola. We got to make sure it's in one of the standard forms. And this one actually starts with the y values first. So let's write the standard form for that. Y minus k quantity squared over, let's see here, a squared minus x plus 6 quantity squared over b squared is equal to 1. So in our case, we could see the center. I'm sorry, I didn't mean to write x plus 6. I'm going to write the general standard form. The standard form here would be what? X minus h. So let's label the center hk, which equals negative 6, 3. And then we have our a's. A is equal to 5, and b is equal to 1. And what do we have now? We are going to graph this hyperbola. And the key, of course, is to graph the center first. A graph paper would be really, really good here because we're actually going to draw some dotted lines that are associated with this hyperbola. So let's graph the center. Negative 6, 3. 1, 2, 3, 4, 5, 6. Negative 6 is right here. And then 3 units up. So right here is my blue star. That is the center. Now from there, we're going to draw a little rectangular box. And that rectangular box, we want to first draw 1 unit left and right. And we'll start drawing this rectangular box 1 unit left and right. And how far do we have to go up? Well, A is 5, so we're going to go 5 units up. 2, 3, 4, 5. And so you have this little narrow rectangular box. So 1, 2, 3, 4, 5. And I'm drawing it dotted. That's going to be key. This hyperbola, because the y values are first, this hyperbola is going to have 2 branches opening up and down. But how do we locate those 2 branches? Well, now we crisscross this this rectangular box. It goes up 5, right 1. 1, 2, 3, 4, 5, right 1. About here. I can go down 5, left 1. 1, 2, 3, 4, 5, left 1. About right here. And these are actually asymptotes. So I can draw another asymptote going the other way. I gotta go down 5. 1, 2, 3, 1, 2, 3, 4, 5, right 1. Right there. Gotta go through this corner. And then I'm going to go up 5, left 1 on this side. 1, 2, 3, 4, 5, left 1, right about here. So there are your asymptotes. You may have remembered these were called slant asymptotes in a different context. Now, because this is opening up and down, I need to locate the vertices. There's a vertex here. Let's label that. That's actually negative 6. 1, 2, 3, 4, 5, 6, 7, 8. And there's another vertex here. And let's label that as well. That's negative 6, negative 2. So there's the vertices. And then the 2 hyperbolic branches are actually approaching your asymptotes. But they don't cross. You don't cross those asymptotes, just approaching them like that. Make sure you remember to put the arrows on them. And there you go, you're done. Let's go ahead and graph this hyperbola. First thing you want to do is make sure it's in standard form. And if it's in one of your standard forms, you might as well write it. Let's write the standard form out. X minus h quantity squared over a squared minus y minus quantity, let me say that again. Y minus k quantity squared over b squared is now equal to 1. Let's locate the center. Our center is what? H comma k. In our context, it's parentheses negative 2 comma 6. Let's go ahead and graph that. Negative 2 and then up 6. 1, 2, 3. And let's locate that with a blue star. Now we also know A. A is 5. And we're going to make a little rectangular box that is 10 units wide and, let's see, 8 units tall. How do I know it's 8 units tall? Because B is 4. So we're going to make a little rectangular box now. We got to go 5 units to the right. 1, 2, 3, 4, 5. And right there, I'm going to start a rectangular box. 1, 2, 3, 4, 5. Another rectangular box. Now I need to know, well, I need to go 4 units high. 1, 2, 3, 4. And I make this rectangular box with a dotted line. Maybe I should use this color to make it stand out. Well, that didn't help out that much. Make a little dotted box. 1, 2, 3, 4. So I need to turn right here. And if you have a straight edge, what you're going to do now is draw the asymptotes. Go ahead and draw the asymptotes. So you drew the asymptotes through the corners of the rectangular box. Make sure you draw dotted lines, put the arrows at the end. We're going to now use these asymptotes to graph the actual hyperbola. Now, since the x values went first, the quantity x plus 2 went first, these hyperbolic branches are going to open left and right. And there's actually a vertex here and another vertex here. They're left and right of the center. And we're just simply going to draw the hyperbolic branches. So sometimes, you do see hyperbolic patterns. Satellite dishes sometimes follow a hyperbolic pattern. The curve of a satellite dish might actually be hyperbolic. The path of a comet is often hyperbolic. So these hyperbolic graphs actually have a very, very distinct shape. And there you go. You have actually graphed the hyperbola. All right, let's graph this hyperbola. It's given in a very general form or generic form, and so we can't recognize the A, B's, H, and K's yet. The goal here is to get this into one of the standard forms. And we're going to use the most popular trick, well, or at least one of the most popular tricks in mathematics, and that is called completing the square. Why don't we do that? -4. I'm going to factor out x squared here. Actually, I'm going to highlight that. I'm going to emphasize there that we're completing the square on x squared minus 2x. We'll leave a space there. Put parentheses. Now we're going to go ahead and complete the square on y squared minus 8y. And we'll leave a space there. Let me change colors here so I could emphasize that we're completing the square on y squared minus 8y. 8y. And we're going to put the subtract 8 to both sides. I don't want that constant 8 on the left-hand side of the equation. We're ready to complete the square. Remember, completing the square, divide this middle term by 2, which you get to be 1. So 2 divided by 2 is 1, square 1, and then we're going to put it right here. Now, all of a sudden, you can't subtract 4 on one side of the equation. You got to subtract 4 on both sides of the equation. We're going to go ahead and complete the square here. Y squared minus 8y. Divide 8 by 2, you get 4. Square it, you get 16. This time, you did add 16 to the left side of the equation, So we're going to add 16 to the right-hand side of the equation as well. Remember, you subtracted 4 because you have to account for this distributive property. All right, why did you complete the square? So that you can see perfect square trinomials. Here's a perfect square trinomial. And then there's another perfect square trinomial. So now you just factor, which is now equal to 4. This is almost in standard form. We're going to go ahead and write the positive coefficient first. So y minus 4 quantity squared is positive. And then we're going to say subtract 4 times what? X minus 1 quantity squared is equal to 4. Just a little rearrangement there. And then we're just going to react to the problem. Divide the entire sides by 4. Because 4 is not 0, we're going to do common denominator. Y minus 4 quantity squared is now over 4 minus x minus 1 quantity squared, which is now equal to 1. There is our standard form. I'm going to circle that. We're going to need this, very much so. Let's identify our center. It's 1, 4. And we need our A. Our A is underneath the Y's. So A is 2 and B is 1. And that will help us draw a little rectangular box. Let's graph 1, 4. There's our blue star. I should draw the axes. X-axis. Here is what? The y-axis. And what do we got? We need to travel 2 units up and down. So we're going to draw a little rectangular box that is that has the width of 2 and a height of 4. So it's rather small. I'm just going to draw a dotted right there. It's running parallel to the y-axis. There. Now go ahead and draw the slant asymptotes, or the asymptotes. And remember, the asymptotes for a hyperbola goes through the corners of that rectangular box. You go ahead and do that. So you drew your asymptotes through the corners of that little rectangular box. And now we're going to go ahead and locate the vertices. Since the y quantity appeared first in your standard form, our vertices are right here on the box. Let's go ahead and label that. So this one is 1, 2, and this one's 1, 3, 4, 5, 6. So there are your 2 vertices. Go ahead and draw your hyperbolic branches. They have to approach the asymptotes, and they don't cross. Make sure you put arrows at the end, because that means they will approach that asymptote forever. It just keeps going, keep going, and keep going. And there is your hyperbola with its 2 hyperbolic branches. Make sure you could show your work. Make sure you can complete the square. Make sure you can identify the center and your values for A and B. Finding the foci of a hyperbola. Given an equation in its general form, let's find the foci of this equation, or this hyperbola. We first need to get it into one of its standard forms. So let's complete the square to do that. So let's factor out a -4. And we're going to go ahead and complete the square on some kind of x squared plus beta x, or x squared minus beta x. We have a plus 6x. And we're going to leave a space there. we'll leave a space there to complete the square. What else do we have? We have a plus 9, and then what do we have left? We have a y squared minus 2y. And then I don't want that 63 on the left-hand side of the equation, so I'm actually going to add 63 to both sides, and we get 63 over here. Let's go ahead and complete the square. And make sure you balance the equation. So if you're balancing the equation, we have to make sure we subtract 36, and then we add 9. What's 63 minus 36 plus 9? Let's find out. So that's minus 27. That's 63 minus 27. How much is that? That is 36. All right. So let's divide the entire sides by 36. And that is because 36 is not 0. And using common denominator on the left-hand side of the equation, we're going to see some really nice patterns. We're going to see that this is negative x plus 3 quantity squared divided by 9. And then we have plus y minus 1 quantity squared divided by 4 is now equal to 1. That's not quite a standard form. We're going to put a y minus 1 quantity squared first, and then 4 plus what? Nope, not plus. It's a hyperbola. We have to make sure you put it in standard form so that you recognize that it is indeed a hyperbola. All right. Now, to find the foci, we use this relationship in a hyperbola. The relationship is c squared is equal to a squared plus b squared. Pretty convenient. C squared is equal to a squared plus b squared. And so what is really going on? You know, this hyperbola is actually opening up and down. So it's opening something like this. And we're not interested in the vertices. We're interested in the focus points. So remember, there's a center here. So we're trying to find C. C is this many units. And C is the distance from the center to a focus point. Let's find that C. C is actually greater than 0. That means C is equal to the plus or minus the square root of a squared plus b squared. So C is equal to plus or minus, what's a squared? And a squared is 4, and b squared is 9. So C is equal to plus or minus square root of 13. But you know that C is greater than 0. So C must be square root of 13. How do we find the foci? Well, we need the center. And the foci are going up and down, or are located up and down, or located vertically. So the foci is, we have an x, which is negative 3. And then we have 1. 1 plus or minus root 13. And the reason for that is because the center is negative 3, 1. Now that's not a good way to write two focus points. Let's write our foci a little bit differently. Let's write them separately, make them really, really clear. -3, 1 plus root 13, comma, and then -3, 1 minus root 13. There are your foci. Find an equation of a hyperbola having foci at 2, 3, 10, 3, and vertices at 5, 3, and 7, 3. This is a hyperbola opening left and right. So I'm going to just draw a quick sketch of that. I don't really need to be very accurate. I just need to give myself some intuition. We have the vertices. The vertices are right here. 7, 3, and then 5, 3. We also have 2 focus points. So focus points are in here. They're not on the hyperbola, but they help, represent the curvature of the hyperbola. So the vertices are what? 10, 3. And we have 2, 3. We should be able to find a center with this much information. Let's take the long distance here. The long distance is 8 and divided by 2. So if we do 8 divided by 2, we know the center. This has to be 6, 3. Yes, that is 6, 3. So we have HK, which is equal to 6, 3. Do we have A or B? I think we even have C. C is 4. We do have C. C is 4. Remember, C is the distance from the center to a focus point. Do we have anything else? I say we do. We actually have A. A is going to be 1. A is 1. How do I know A is 1? Well, this is A right here. Yeah, how do I know C is equal to 4? Right there. This is C equals 4. Right? 10 minus 6 is 4. All right. The only thing left we need for the standard form of a hyperbola is B. And we could find that. That's not a problem. We know the relationship. C squared is equal to A squared plus B squared. So B squared is equal to C squared minus A squared. Why don't we find B squared? B squared is now equal to 16 minus 1, which is 15. B squared is 15. That's what we want anyway. What do we got? X minus 6 quantities squared over 1 squared. So I don't need to write the invisible 1. Why don't we keep it invisible? Let's write the minus symbol. Y minus k, which is 3 quantities squared, over 15. And set that equal to 1. And there you go. You have written the hyperbola in standard form. And that's really the goal. Let's circle our final answer. Make sure you show how you get B squared. Make sure you show that work. That is necessary.